Now next we are going to discuss about integral property of a Laplace transform. Means if we have a Laplace transform of any function, then what is the Laplace transform of an integral of that function, provided the integral will exist. So again I repeat the statement, previous statement, ft and f dash t must be from the category of a class A function, must be from the category of a class A function. So here what is the statement of a Laplace transform of an integral? What is the statement of a theorem? If Laplace transform for ft equal to fs, then Laplace transform for 0 to t fx dx equal fs ds, fs ds. So here in order to prove this theorem, here already we assume that ft is from the category of a class A function. So let what? Let zt equal, let here zt equal 0 to t fx dx, fx dx. Let a function zt equal to 0 to t fx dx. Now what is a z dash t? Z dash t equal what? Z dash t equal ft, z dash t equal ft. Now what is the value for z0? z0 equal what? If we put t equal to 0, 0 to 0, so what is the value of integration? The value of integration become 0. Now in order to prove this theorem, we use the property of a derivative of a Laplace transform. So what is the property of a derivative of a Laplace transform? If we apply on a function gt, Laplace transform of a z dash t equal s Laplace transform of a zt minus z0 minus z0. So here we write what? Here we write a Laplace transform for gt and Laplace transform for g dash t equal s Laplace transform for gt minus z0, using the property of a derivative of a Laplace transform. Now here we put the values of a z dash t, zt and z0 from these expressions z dash t and z0. So if we put these values in the next page, then Laplace transform of a z dash t. Z dash t is a what? G dash t is a 0 to t fx dx, this one equal s naught. So I think we put the wrong value. So what is the g dash t? G dash t is a ft. So if we put the value for z dash t, the value for g dash t, this one is a Laplace transform for ft equal s Laplace transform of gt, and gt is a what? Gt is a 0 to t fx dx minus z0 with a 0, z0 with a 0. So Laplace transform for ft is already given. Laplace transform for ft is given. What is the Laplace transform for ft? Here we assume that Laplace transform for ft is a fs. So here we put the Laplace transform for ft. This one is a fs. Fs equal s time of a Laplace transform of 0 to t fx dx. Fx dx, after simplification, Laplace transform of 0 to t fx dx equal fs upon s, proved. So, if we have a Laplace transform of ft, then we able to find out a Laplace transform of a 0 to t fx dx. So, what is the Laplace transform for integral? Means a Laplace transform for 0 to t fx dx equal fs upon s, where fs is a Laplace transform for ft. So, based on a property of a integral of a Laplace transform for any function, now we are going to solve two numerical example. So, here in order to save the time, already we write two problem. What is the first problem? First problem is a proof that Laplace transform of a 0 to t sin 2u du equal 2 upon s into s square plus 4. And second one is a evaluate 0 to t sin x upon x dx. So, first we solve the first, we prove the first, we take a first problem and try to prove this result using the property of a integral of a Laplace transform of a any function ft. So, here now we assume that ft equal, let ft equal sin 2t, sin 2t, sin 2t. Now, what is the Laplace transform of this one? Laplace transform of a ft equal Laplace transform of a sin 2t. Now, we know that when we find the Laplace transform of elementary function, the Laplace transform of a sin ax sin at is a upon s square plus a square, and what is the value of a here? The value of a is a 2. So, this become Laplace transform of sin 2t become 2 upon s square plus 2 square means a 4, provided s is a greater than 0. S is a greater than 0. Now, by integral property, integral property of a Laplace transform, Laplace transform of a 0 to t sin 2u du equal fs upon s, fs upon s, where fs is a what? Fs is a Laplace transform for ft, and ft is a what? Ft is a sin 2t. So, Laplace transform for ft is a sin 2t equal 2 upon s square plus 4, s is a greater than 0, and we denote this one is a capital Fs. Now, if we put the value of Fs here, this become what? 1 twice upon s into s square plus 4. So, this one is a similar to this expression. So, now we able to prove this result, be able to prove the first result using the integral property. So, it is a very simple, just identify ft. This means this expression is a nothing else. We assume that this one is a fx, then corresponding value is a ft. Once we find the Laplace transform for ft, then using the integral property, we divide by the fs of a Laplace transform for ft, then we able to find out a required result. Now, we try to solve a second problem. What is the second problem? Second problem is a evaluate 0 to t sin x upon x dx, sin x upon x dx. Now, here again how we find the solution? In order to find out the solution, let ft equal, this expression is assumed as a ft, function of a t. Here this one is given as a function of a x. So, if we write as a function of a t, then this become ft equal sin t upon t, sin t upon t. Now, Now, Laplace transform of a ft, Laplace transform for ft equal Laplace transform of a sin t upon t, sin t upon t. So, how we find the Laplace transform for sin t upon t? We know that Laplace transform of a sin t equal what? Using the formula of elementary function, Laplace transform for elementary function, Laplace transform for sin t become 1 upon s square plus 1. Laplace transform for sin t equal 1 upon s square plus 1, and again using the property of a division by t, the Laplace transform of a sin t upon t, sin t upon t equal what? Equal s to infinite fs ds. And what is the fs here? We assume that s is a greater than 0, this one equal what? Here we cannot say this one is fs because ft, here we assume that ft is a sin t upon t. So, Laplace transform of ft is fs. So, here Laplace transform of a sin t upon t is as s to infinite Laplace transform of a sin t ds, sin t ds. So, this become what? This become s to infinite and Laplace transform for sin t is a 1 upon s square plus 1 ds, s square plus 1 ds. And we know that integration of a 1 upon s square plus 1 with respect to s is a what? Tan inverse s. So, in the next phase we write what? We write Laplace transform of a sin t upon t equal s to infinite 1 upon s square plus 1 ds, this one equal to tan inverse s, and what is the upper limit and lower limit? S to infinite. If we put the upper limit, tan inverse infinite minus tan inverse s. So, tan inverse, as we know that the value of a tan inverse infinite is what? The value of a tan inverse infinite is a pi by 2 minus tan inverse s, and this become cot inverse s. So, this one is a Laplace transform of a sin t upon t equal cot inverse s, and here we denote this Laplace transform of a ft is a Laplace transform of a ft is a fs. So, this one is fs. Now, again using the integral property. Now by integral property, what will happen? Laplace transform of 0 to t sin x upon x dx equal what? Laplace transform for 0 to t sin x upon x dx equal fs upon s, where fs is a Laplace transform for ft. So, fs upon s. So, what is the Laplace transform? This become 1 upon s cot inverse s. So, this one is the answer. This one is the answer of a second problem. Answer of this one, evaluate 0 to t sin x upon x dx, and answer is a what? Answer is a the Laplace transform of 0 to t sin x upon x dx is a 1 upon s cot inverse s. So, this one is a what? This one is a application of integral property of a Laplace transform. How we find the Laplace transform of a integral of any function if we have a Laplace transform of that particular function. So, this one is the integral property.